So we've seen the Bernoulli distribution, the binomial distribution, and the geometric distribution. And the last distribution for this section is going to be a distribution called the Poisson distribution, named after the mathematician Simeon Denis Poisson. So the Poisson distribution is used to model things like the number of times something happens in a set period of time, like the number of emails you receive in a day, or the number of claims at an insurance company each year, or the number of calls to a call centre each day, that sort of number of arrivals. Famously, one of the first uses of this was measuring how often soldiers got kicked to death by their horses, which again is a number of times something happens in a period of time. Now later on in the next subsection 6.4, we'll explain why the Poisson distribution makes a good model for these number of times things happen processes. For the moment, we're just going to write down the definition and worry about why it's a sensible definition later. So the definition is this. Again, we will let x be a discrete random variable. With range, well, the number of times something could happen is it could happen no times at all, or one time, or two times. So this will be any non-negative integer. And its probability mass function is this slightly strange looking thing. It's e to the minus lambda, where lambda is a parameter here. Lambda to the x over x factorial. And this is a Poisson distribution, P-O-I-S-S-O-N, Poisson distribution. And we write P-O lambda for this. In particular, lambda, we call this parameter the rate, because we'll see in a minute that this is kind of like how often the thing happens. We should also notice that we've got an x factorial down the bottom here, where x is allowed to be 0. So I should point out, by convention, 0 factorial equals 1. That's just a rule. So if you see a 0 factorial come up, what that means is 1. It's kind of the empty product of not multiplying anything. So that should be understood to be 1. So we're going to do another example on this, and the example is here. So the example says an insurance company receives large claims at a rate of lambda equals 1.2 per day, modelled as a Poisson distribution independent between days. And here a large claim is one of more than £100,000. So these large claims are arriving at a rate of lambda equals 1.2 per day. What's the probability in a 5-day week the company gets at least one large claim every day? Well, first let's just look at 1 day. So claims in 1 day. And the model is suggesting that this is Poisson with a rate of 1.2 claims per day. So what's the probability that we get at least one claim in a day? Well, that's the probability x is at least 1. Well, we've seen these at least 1 questions before, right? And we said that for at least 1 questions, try looking at the complementary event. So here, this is 1 minus the probability that we don't get any claims. Right? The probability we get at least 1 claim is 1 minus the probability we don't get any claims. But we can work that out in terms of this Poisson distribution. It's e to the minus lambda, which is 1.2, lambda to the x, 1.2 to the 0, over x factorial, 0 factorial. That's 1 minus e to the minus 1.2. Anything to the power of 0, like 1.2 to the 0, is just 1. And 0 factorial on the bottom, we said that that was just 1. So that's 1 minus e to the minus 1.2, which I worked out earlier, it's about 70%. So there's about a 70% chance that on a single day they get at least one claim. But the probability that they get at least one claim all of the 5 days of the week, that's the probability x is greater than or equal to 1 to the 5, because it said in the question that that they're modelling it as being independent between days. So under that assumption, the probability that all 5 days are free of have at least one claim is that probability to the 5. That's 70% to the 5, and I worked that out earlier. It's about 17%. So there's about a 17% chance that they get a claim every day under this Poisson model. And again, would be interested in some facts about this Poisson distribution. So the facts are, well, first, we ought to say that P of x is actually a PMF in that it sums to 1. This was kind of clear by definition for all the other things we've looked at, the Bernoulli, the binomial and geometric. But there is actually something to prove here, right? Because we just wrote down some funny numbers for P of x. Expected value of x is lambda. That's good news. That's kind of why we were calling this thing the rate, right? Because it is really the expected number of times we expect the event to happen. So it seems sensible to call that the rate at which it happens. And the variance, it turns out, it is also lambda as well. So the expectation and the variance have the same value here. So the proof for this is some messing about with sums and remembering the Taylor series for the exponential. So I've given the detail for that in the written notes, and I don't think I'll go through it here, but I do recommend reading the proof because in the written notes I go through the first 2 of these bullet points. But then the third bullet point on the variance is for you to do on the problem sheet. So if you've read through how to do the first 2 in the notes, you should fairly easy to be able to do the third one on the problem sheet and thereby work out the variance of the Poisson distribution.